Good afternoon, friends. This is Mowli. Today, welcome to the session 4 of ARM-based development. As per the schedule, we have finished the unit 1. Now we are getting into the unit 2, where we will be covering the data flow model of ARM and then ARM's 3-stage pipeline. So this is the focus of the session today. We will be touching upon the data flow model. What I mean by data flow model is that when an instruction gets decoded inside the ARM core and how a particular instruction gets executed by interacting with the different registers in the register file and then sending the result out back to the register. And then we will touch upon the pipeline. So this is a new concept which I will be introducing you to. Here in this lecture we will talk about ARM's 3-stage pipeline, which is the ARM 7 TDMI 3-stage pipeline, and then talk about what are the different stages and their limitations in this section. Now to start with, let us again refresh the fundamentals on which ARM processor is designed. All of you are aware that the ARM instructions are all 32 bits long. Okay, so they are all aligned on word. That means the 4-byte boundaries. The instructions can be only on 4-byte boundaries, and all of them are of 32 bits length. And as you are aware, this is a RISC processor with a load store architecture. That means anything to do with memory is done using load or store instructions. That is, if the processor wants to read a particular data from memory, it has to use a load instruction, and if it wants to save any value in the register to a memory, it has to use store instructions. Now all of the data processing instructions, for example arithmetic or logical operation or anything that can work on only register operands. So any of the data processing instructions need to work only with the registers. That means if the processor wants to do some addition of two values which are stored in the memory, first of all the processor has to load those contents from the memory to one of the internal registers which we saw in the last session, and then it can perform addition on those two contents of the register. Once the result is written back into the register, it has to be written back into the memory wherever the result is supposed to go by using a store instruction. So addition cannot be performed directly picking up an operand from a memory, whereas CISC processors support them. And ARM core is a 32-bit processor, and most of the instructions treat the registers as holding a signed or unsigned 32-bit value. So I have mentioned about signed and unsigned earlier. The processor doesn't recognize whether the value which is stored in a register is signed or unsigned. It changes the flags if the instruction allows it to change the condition flags like carry 0 and overflow flag and sign flag, and based on the operand whether it is signed or unsigned, the programmer is supposed to look at the relevant conditional bits to understand the outcome of the result. And all the data processing instructions work only with 32-bit numbers, though memory and the processor they have a provision to read 8-bit or 16-bit data, but when it comes into the register it gets expanded to a 32-bit value, and then any data processing instruction operate on it assuming it has to be a 32-bit value. Now all the decoding of instruction is done using hardware circuitry. This is to make the decoding logic faster. Now let us see how a particular instruction looks like. As I told you, the instruction width is 32 bits. So I have given a sample instruction. Okay, this is add RD and RN and R1. This is a normal convention, the way an assembly instruction is represented in ARM. So add shows that it is an addition, and RN and RM are the two operands. They get added, and the result is put into the RD, that is a destination register. Now these registers could be anything from R0 to R15, and you have to remember that R15 has some special restrictions because that is supposed to be a PC, that is a program counter. Other than that, other registers could be used here to perform this operation. Now how is it encoded into a instruction, 32-bit instruction? So the total width of this is 32 bit. I have not shown all the intricate bit details of this instruction. It is a general format where the function to be performed is there, which occupies f bits in the instruction, and then there are three operands, right? Two operands and one is the result. So three registers are to be represented in the instruction, which each one of them is occupying n bits, because they are all internal registers we are representing here. So all of them require n bits to encode them. Now the three address format, all register specifier are given here as two operands and one destination address. So two are source operand as I mentioned, and one is the destination register. There are some restrictions on some registers which can be used in a particular location based on the type of the instruction, that we will be covering when we touch upon each of the instructions in detail. So this is the general format. Okay. So these three can be any of the available general purpose registers. Now let us see. I told that each of the registers are represented using n bits. You know that the registers are all the general purpose registers which are available in the ARM processor. If you recall, in the last discussion we talked about different modes: user mode, session mode, and supervisor mode, and FIQ and IRQ. So in different modes, overall how many registers are visible, that also we touched upon. So I want you to just spend some time, maybe 1 or 2 minutes, it doesn't take more than that, even less than that. So find out how many bits are required to encode the register which is addressed in these three operands, right? Is it 32 bits, or does it need 8 bits, or 4 bits, or 2 bits? So having guessed, let us see what is the correct answer. It is the option C. That means it needs 4 bits to represent the register. Why do we need 4 bits? All of you know how many maximum numbers can be represented using 4 bits. It is 0 to 15. That is totally 16. So if you recall the number of total registers in the ARM register file in each mode, okay, overall it may be some 37 or so, but when this processor is operating in a particular mode, it is going to be seeing only a subset of the registers which are available physically there. So it happens to be 16. So 4 bits are sufficient to encode which of the registers is used for each of the operands and the destination register. So this has to be a 4-bit value. Okay. Now let us look at a data flow model of ARM. Okay. So this is the diagram which shows the internal structure of how the instructions get into the processor and how they are processed. So let me give an overview of this. This is the data. Where is it coming from? It is coming from memory. Now if you recall, ARM 7 TDMI, which we are talking about now, is a non-environment architecture. So that means one architecture means what? Both instructions and data come from the same memory. So here data also come as well as instructions also come into the processor this line. Now the instruction gets decoded, and based on the opcode and based on the operand registers mentioned in the instruction, there is a decode logic generates some control signals to transfer information between one register to other. Okay, so that is a decoding logic which does, and then during the execution, some of the registers get opened up and the data flows into the proper registers, and the instruction get executed. Now, leaving aside that part, let us understand the other portion of the circuitry here. The memory write, anything to be written into memory has to go through this data bus, and one of the registers contents need to be written into. So there is the flow of data from here. Memory write goes through this, and any memory read, if you recall in the last discussion, we said it could be a 8-bit content or a 16-bit content can come from memory, and optionally it could be sign extended based on the type of the data which is coming in, and finally what is written into a register has to be a 32-bit data, because I told you the instructions operate on only 32-bit data values, 32-bit values in the register. So even if memory interface allows reading a 8-bit or a 16-bit data, that either gets sign extended or it's filled with 0, the top portion of the content, and the complete 32-bit content of the register is used for any arithmetic operations inside the processor. Now our key register is PC here, program counter, which is also part of this register file. So whenever the processor wants to access the next instruction, it has to send that content of R15 or a PC into an address register, which is interfaced to the address bus of the memory. So address goes out. So the address which is going out could be an address of an instruction, or it could be an address of a data. So if there is a memory read, the address goes out here and the data comes in through this. If it is an instruction, address goes out from here and the instruction come in to this bus, data bus, and goes into the decoder. So this is the flow of address and the data. Now, why is there an incrementer here? You know that the PC needs to be incremented on completing one instruction. Accessing after one instruction, it has to be incremented. Now, incremented by how much of amount? It has to be 4, because we are reading 32-bit instruction from the memory. That means 4 bytes of data. So when the next instruction needs to be read, it has to increment the address by 4, and then that value is put back so that the processor can keep on reading instructions from the memory. It can perform only instruction access provided there is no memory access in the instruction. But suppose we have a sequence of instructions which are all arithmetic instructions like add or subtract or any or operation which is internally done with the register content, and there is no need for accessing any memory, then the processor can keep on sending the PC value to access the instructions, and it can keep on incrementing it. If there is no other jump or branch to some other address, then it can sequentially access the address in the memory, the instructions in the memory, and then keep on processing it inside. But no instruction sequence could be like this, because we need some data to be processed, and that needs to be written back into memory or read from the memory. So our instruction flow will be interrupted with some data accesses also. So during that time, what happens is the instruction access is deferred and the address, the data access is done. So everything happens in one cycle. So either in one cycle it reads an instruction, or it read or write the memory content or data content. Okay. So this is about instruction flow. Now what happens? Now this value needs to go here. Why? Because this is actually a content of a PC which needs to be written into R15, which is a part of register file. So not only this instruction address goes into the address registry, it also goes into the register file to be written into R15. Now in the register file, you see how many read ports are there. There are so 2 operands are read from here, and then one result is written into register file, and R15 is read from here, and the incremented R15 is put back into register file. Again, if you remember, I mentioned that a register file here in ARM has 2 read ports and 1 write port for the registers other than R15, and there is one special read and write port for R15. So all these operations, reading 2 operands from the registers and writing the result back, and reading the R15 content and writing back, can all happen in one cycle also, because register file has that many ports available for the access of these values. Okay, let us this much of introduction is enough. Let us go through one by one to summarize what I said. So if from the memory we are reading 8-bit or 16-bit number, it needs to be extended to 32-bit based on sign, whether it needs to be signed or unsigned value. It will be, if it is signed, it will extend the MSB bit into all the high-end values, or it will fill it with zeros while extending the number of bits. Now, how do we know whether what is read from the data memory is a signed or unsigned value? It can be represented in the instruction, and the programmer knows what the value he has stored, whether he has stored or read, signed value or unsigned value. Based on that, when he is reading that particular content from the memory, the instruction he can mention whether it is a signed value or an unsigned value. Or based on that, the signed extended circuitry will come into play. Otherwise, it will directly write the value into this and then fill it the higher bit with the zeros. And 2 source operands for any instruction, A and B paths, are read by these 2 read ports from the register file. And the PC value, as I mentioned, it gets read from here and it is latched here, and the incremented value is written back into register file. So what happens is, suppose the PC is interested in accessing the address, instruction stored at address 1000. 1000 is written, and that goes out in the address bus, and incremented 1004 in the next cycle gets overwritten here, and it also gets written into R15. So what happens is, after reading the instruction at 1000, 1004 gets written into this through this, and it can access this instruction stored at 1004. Okay, that's the way instruction gets accessed. So the address is also written back into the address register as well as R15. Now let us see, what does the ALU do? ALU has an option to take 2 operands. It could be anything, right? RM could be anything from R0 to R15, subject to some restriction based on the instruction which is being executed. So ALU knows based on the opcode what is written, which operation is supposed to do, and relevant is the registers contents are put on these buses based on the decode logic after decoding the instruction, and then the operation is performed and the result is written back into a relevant register based on the instruction. Now it could be a data processing instruction which operates on the register, or it could be a load or store instruction. That means what? A particular register content needs to be read from here, and that needs to be written into a particular address. Now the address may come from one of the existing registers, and there are different addressing modes that we will talk about that when we touch upon the addressing modes. But suppose there is addressing mode which has got some index incrementing, then the incrementing also happens here, and that address goes out, and the data what is to be written goes out through this part. So during the data read or write, these circuitry don't come into picture, and the data to be written goes out from the register file into the data bus through this part. Okay, this is the explanation for load and store instruction, how it gets executed here. Now another important feature is about barrel shifter. Now I told you that during the data processing instruction there are 2 operands read from the register file. Now the second operand, which is properly within the ARM called as RM. So this is a convention followed. Okay, There is nothing special about it, but the RM is one of the operand which only goes through the barrel shifter. So within the cycle, whatever the content of a particular register gets shifted or rotated or some logical operation is performed using this barrel shifter, and the output of that is fed to the ALU. So if suppose addition is to be performed from R0 comes from here, and then you give an instruction saying that the other second operand R1 is read and shifted by 4 bit to the left, and then it is the content of that is added to the R0. Then what happens is that shifting by 4 is done by this barrel shifter, and the shifted value is given to ALU, and the arithmetic addition is performed, and in the same cycle you will say that the output result needs to be written into some register, maybe R2. Then the output is written into R2. So this all happened in one cycle. That is, when we say cycle means we are referring to the M clock that is feeding into the processor. So the complete arithmetic is done, addition is done. Option is based on the instruction the barrel shifter will be used, or it could be a short circuit. But suppose if you say add R0, R1, and then I want that to be written into R2, then R0 R1 come directly there, and then the result is written into R2. So this is the way barrel shifter is used in the processor. So the barrel shifter and the AL can calculate together a wide range of expressions. Okay, and the load store, as I mentioned, there are in the memory there are non-sequential access and sequential access. Sequential access means in the sequential access cycle, multiple address data locations are either read or written in the memory by one single instruction. So what happens is during that time, suppose assume that there is an instruction which says that starting from 1000 access remaining 10 bytes, sequential bytes, the sequential words from in the memory, and then you copy from R0 to R5. So some 5 or 6 register content needs to be copied to 5 or 6 locations in the memory. Now what happens is the address is automatically incremented by 4 starting with the first access, and the remaining accesses also completed in the sequential mode. So to perform the sequential access of memory, this particular incrementer and the address registers are used for the data access. Now we mentioned that a whole lot of operation is getting done in single cycle. So what does that single cycle mean? The M clock, when I say it starts from here and ends here. Now normally you would have seen a clock going up and down and then again going up and down. So we call from the single clock signal we say that one cycle is done. But in ARM it is done in a very innovative way. There are two signals, okay, which are offset by a small time gap and they are not overlapping. That means though these two signals are coming from the common source inside the processor, after this signal goes down, after a finite gap, this signal goes up and then again comes up. So these two signals correspond to one clock cycle. Okay. Now what happens during this time? Why is it required? First of all, the entire circuitry in the data path of ARM doesn't operate on edge trigger. So these are all level triggered and is implemented using a transparent logic or a D flip-flop, which you might have heard about in the digital design courses. So when the signal is high, some part of the circuitry gets activated, and whatever is there on the bus, internal buses, the signal gets transferred to the circuitry. It could be a register or it could be ALU or whatever. And then another set of circuitry in the processor gets activated when this is high. So they are all triggered by, enabled by this signal. So why is it required? Because if suppose you allow one set of clock circuitry to get activated by using this, and then when it goes low, the remaining set of instruction circuitry gets activated. Because of this transition, there can be a race condition where one need not have switched off and one need not have switched on. So there may be a possibility of mix-up. So they have decided and built the system using two different clock cycles which don't overlap at all. So anything which is on during this time is completely off, and anything needs to be on comes up during this time. Now let us see how this is useful for reading the values. If you recall these two. Suppose you assume that these two signals are coming and the barrel shifter is ready to accept the data which is coming in through RM. Now when the first clock goes, phase 1 clock, when it goes up, the register read time starts and the contents of the register file, selected registers, are available on the bus, and ALU reads it, one of the parameters, RM gets read, and RM could be either passing through a barrel shifter and then comes to the ALU, or it could be directly read from the ALU. Now what happens is, during this time the ALU is open to receive the operands coming from the register file. Either RN, which is directly connected to from register file to ALU, comes directly here, it is available, whereas the next operand RM could go through the barrel shifter and it might come with a little bit of delay. So ALU will wait for this particular time for both the operands to be latched. So this actually allows time for the barrel shifter to do its job and make the result available in the same clock. So immediately after getting both the parameters, ALU operates on it, either it could be add or arithmetic or multiplication, whatever, subtraction operation, and then the result is available here, and during that time this phase 2 is active, and during this the register which is supposed to be reading the output coming from ALU is open and the result gets written into that register. So from this start of time to the end of the time, what happens is the operands are made available to ALU, and one of the RM operand can go through barrel shifter, and that's also made available to ALU, and the ALU performs the operation during this gap, and when the result is available before the end of this phase 2, they get latched. So all these operations get performed in one cycle. Now a little bit of explanation here for your understanding. This register read buses are dynamic and they are pre-charged during phase 2. What I mean by pre-charged means the buses which are connecting the ALUs and the register file, they are of special nature and they are called dynamic because the buses are getting pre-charged, and then when a particular register is driving them based on the values of the register content, either is 0 or 1, the pre-charged bus gets discharged wherever the zeros are, and then the result gets latched onto it at the beginning of the next clock. So basically this is provided to enable the access of data, and the preparation for the data can be done in one cycle ahead, and at the end of phase 2, the whichever buses are required to feed the data for the next phase, they are ready with the contents. So when phase 1 goes high, the selected registers, the phase 1 when it goes high, the selected registers discharge the read buses. That means when I say selected registers discharge, that means they put the values on the bus. So when the phase 1, during the phase 1 they are discharging, that means in the prior cycle the bus is already charged, and when the particular register needs to drive the bus, they discharge the specific bits in the bus or lines in the bus based on the content of the register, and then they get latched to the circuitry which is enabled using this phase clock. Okay, whichever the transparent latches, they get enabled. So this is the way two-phase non-overlapping clock functions in ARM processor for transferring data between registers and the ALU or barrel shifter within the ARM processor. Now ALU has input latches which are open during phase 1, okay, as I mentioned, and allowing operands to begin combining. What I mean by operands to begin combining means ALU gives sufficient time for both the operands to be available. In case the second operand needs to come from barrel shifter takes some few nanoseconds to perform its operation. So it allows both operands to be settling down after the barrel shifter operation is done before latching on the value at the end of this phase 1. So, but they close at the end of phase 1, so the phase 2 recharge can happen for the next phase 1 clock. So ALU then continues to process the operands through phase 2, producing a valid output towards the end of phase 2, which is latched into the destination register at this point. So within the clock, what are the operations done? This is the 1 clock cycle. Okay. So to summarize, what are the operations done in a single clock cycle? ALU reads the operand Rn. Second operand Rn is either read directly or through barrel shifter. ALU operation performed, result is sent out, and it is latched onto the RB. All the above operations correspond to the execution part of an instruction. Please remember that this is part of an execution part of it. So they are happening 1 clock cycle. So this is the summary of how an instruction gets executed. That I explained the clock as well as the data flow of inside the processor. Now let me introduce you to the pipeline concept and how it maps onto the data flow that I explained just now. Now just generic definitions of pipelining. All of you might have heard something about pipelining in your undergrad class, but even if you have not heard anything at all, this will be a good refresher for you to understand what the pipelining means. This is an implementation technique where multiple instructions are overlapped in execution, so which is not visible to the programmer. So from the programmer perspective, instructions get executed in one clock cycle, but internally it is divided into multiple and then they get executed. That we will talk about how it is done. So each step in the pipeline is called a pipeline stage or pipe segment, and the pipeline machine cycle is the time required to move an instruction from one step of the pipe to the next step. And throughput of a pipeline is the number of instructions that can leave the pipeline in each cycle. Okay, and just for a moment you remember this, but it will get clear when I explain the concept here. So latency is an instruction needs some time, finite time to pass through the pipeline. So based on the number of stages in the pipeline, the latency could be either 3 cycles or 5 cycles. Whether it is a 3-stage pipeline or a 5-stage pipeline. Let us see how it is implemented. Let us first see why is it required. Now suppose a particular task. Here task I mean is that anything could be an add instruction or a null instruction. But for simplicity's sake, let us take an add instruction. Suppose it takes, with a processor which doesn't have any pipeline, it takes 3 seconds. Then you divide the operation of add instruction. So now what are the operations involved to perform an add operation? First of all, the add instruction needs to be fetched from memory and it needs to be decoded, as I showed you the decode logic inside the processor, and based on the decoding, the relevant registers are to be accessed, and the operation, if it is an add or subtract, needs to be performed during the execution cycle, and the result needs to be written back into the register. So that is all happening in the execution cycle. Now, instead of doing them in one go, they are split into 3 stages, and they all happen at 3 points, 3 different circuitries. Okay, fetch, decode, and execute. Each one of them feeding on to each other. Now, you assume that if T is the time taken for all the operations, if you want to perform the same thing using 3 stages, you need to divide them into k subtasks. Now, any task which is divided by some amount will take less time, right? Because if the whole thing takes 3 seconds, suppose, then if you are dividing into 3 stages, then each one of them may take 1 second. So we are actually, the time taken per stage would be now coming down by number of stages and the total time it took initially for performing that operation. So it is needed here. Now what does it mean? That means that any data transfer between 2 stages in the pipeline needs to happen in this time. That means it's much faster than the original time, the t. So if suppose there is a sequential instructions which are there and they keep coming into the pipeline, the first instruction come inside, there is nothing here, so assume that it is the processor is powered on, so there is no, the pipeline is empty and the first instruction come in. First instruction will be only here, so nothing is coming out of this, and then second instruction when it comes in, the second instruction is fetched here and the first instruction moves to the decode stage, and in the third cycle third instruction gets fetched and the second instruction enters the decode logic and the third instruction comes to the execution stage. Now after end of third cycle, the first instruction which came in has completed the execution. Now what happens after fourth cycle or after the fifth cycle? You will see that the instructions get completed and they keep coming out every t by k time frame. So now you see that earlier the instructions were coming out every t second, now it will come every t by k seconds. That means it gets executed faster, right? At least throughput is more than the earlier stage where there was no pipeline. So after k cycle, one instruction or a task gets completed per cycle. So pipelining is most suited for instruction processing because the instructions are always sequential and they are accessed from the memory and they are fed into this pipeline and they come out through the pipeline after they are completed. Now let us see how I can explain you this. In a non-pipeline implementation, you see that one instruction come in and it takes a whole lot of time, few seconds, maybe I can call it as t nanoseconds because all the processes are running in hours and every but for a discussion point of view, let us say few seconds, and then they come out here. But if they are divided by 3 stages, that means the original time will be divided by 3 now, and after first 3 instructions come or after 3 cycles, you will see that every t by 3 seconds one instruction comes out. One instruction comes out from the pipeline. So the effective throughput is k times faster than the non-pipeline case. So now what happens? The clock, the M clock which was originally between the whole stage, it has to be much faster than the earlier thing. So every clock, the information about the particular instruction will passed on to the next stage. So it has to be done at a speed 3 times faster than the previous speed. And if the pipeline is making the execution faster, the accessing the memory for instruction to get the instructions from the memory also becomes faster. So memory needs to be better compared to the previous stage so that it can feed at the speed at which the processor wants the instructions from the memory. So memory also needs to be k times faster. Let us see. Let me explain how a 3-stage pipeline is implemented in the ARM core. So what is a fetch cycle? The fetch stage is an instruction is fetched from the memory and placed in the instruction pipeline. So the 32-bit value read from the instruction memory is brought from the memory and kept inside inside the data flow machine. It is nothing to do with the visible instruction, visible register. The instruction is kept in the instruction register or some other security which is not visible to the processor. Now decode is understanding the instruction based on the format of the instruction. I told you 3 parameter or 3 operand format, and then there is a functional code which also tells about what operation the particular instruction is expected expecting from the processor to be performed. So that information is decoded. Now why do we decode the instruction? Because only the instruction has the information about what are the operands, which registers are the operands, and which register is the destination register, and what is the operation. All of them, all the information is available when the particular instruction is decoded, and that information has to be communicated to the data flow during the execution so that relevant registers get opened up and the data parameters are passed on to the ALU and the results are returned back to the register file. So respective control signals for enabling a particular register content to be available on the bus and then the ALU output to be returning to a particular register, they all happen based on the control signals coming from the decode logic. So always the execution stage follows the decode logic, and the execution stage owns the data path. That means flow of data between the ALU and the register file happen during this time, and what are the signals to be used during the execution stage is decided by decoding here. So the decode logic passes on that information to the execution stage and that get executed. Now let us see, during the execution, as I told you, it owns the data path and particular instruction gets really executed here, and the values are written into the respective registers as per the instruction that was read. Now it's a twist time again. I'm asking a simple question there. M clock corresponds to which one of the options here? Okay, so this is a kind of stage where every stage takes t by 3 seconds or whatever unit time unit you can think of. Now M clock has to run at t or t by 3 or 3t or none of the options are right. Please spend some time and choose one of the options. The correct option is B. Why? Because M clock is a signal which is going to the memory also, right? So as I told you, two-phase signal, that whole thing corresponds to M clock. So within that, the memory has to provide the instruction, and within the clock the execution has to happen. So t by 3 is the time that is taken for every stage to execute a particular instruction. Okay, so the correct option is t by 3. Now just to summarize what all happening in an instruction pipeline, this is a fetch stage. This decode understands what is the operation to be performed, what are the registers to be selected for the operand, and during the execution stage, as I mentioned during the data flow explanation, registers are read, the A and B buses from the register file, the registers are read by the ALU, and barrel shifter performs the shift or rotate operation, and the ALU performs any operation that needs to be done on the two operands, and RN and RM, and the RD gets written into it. This all happen in one cycle, as I explained you through a two-phase non-overlapping clock cycle of R. So this is what is the operation done in each stages, and this thumb instruction, please refer it. We will cover it later. Now just to make it easy for you to understand, at each stage 3 different instructions will be in the different stages. Okay, not the same. Once the one instruction has flown through the pipeline completely, there will be one instruction here, and the next instruction which was there in the memory will be in this decode logic, and the instruction next to that will be in the fetch logic. Okay, so different instructions are there on each stages of the pipeline. So if a simple data processing operation is done, one instruction gets completed every clock cycle. So how many latency? 3 clock latency is the time taken for one instruction to go through the pipeline and come out of it after the execution. Now when a multi-cycle is executed, the flow is less regular as shown below. So what is a multi-cycle instruction? As I told you, there could be a sequential access of memory, and one instruction can perform copying or taking multiple values from memory, or transferring multiple values between registers, set of registers, and the memory. So during the multi-cycle operation, take an example. In that case, what happens is the execution part of that instruction gets extended. Okay, let us not worry about that too much here. Only suppose you assume a store instruction. This is the following instructions are coming from the memory. The first one was add. Okay, it was fetched in this clock cycle, and it moved to decode during the time fetch. An str instruction was fetched from the memory. Str is what? It's a store instruction. That is enough if you understand that it is a store instruction. That means what? It is supposed to copy a particular value in the register to a memory. Now assume that there are other add instructions which are following after the store instruction. Now let us see go through the thing. Add instruction takes a single cycle. They go through this and complete it after the third cycle. Okay. Whereas fetch instruction takes one more additional cycle. Why? Because based on the str instruction, it could be different addressing modes could be there, indexing could be there. So the address which is there in one of the registers could be added, and then the final memory address that needs to be accessed will be calculated. So during that time, the ALU is also used. So because of that reason, you cannot have any other instruction coming in here. So because this instruction is taking one more cycle to compute the address from where to which the register content needs to be stored. So after the computation of the address, the value will be put in the address register and the actual transfer of register content to the memory happens. So what I am saying is, when some instructions take more cycles, when I say cycle, it means the cycle time of m clock, which is a cycle time for one stage of the pipeline. The remaining instructions get blocked till they complete it. So during this time you see a gap, and then the decode starts. Now why is there a gap here? Because decode of this is happening, so decode of another instruction cannot happen here, right? Because it is getting fetched here. After the decode, after this decode is completed, only this decode can start. Because if you draw a vertical line with respect to time, only one fetch unit can be used in one of the instructions, and only one decode will be there in one of them. Or here there is no decode because this is occupying the decode, because it is generating a signal required for the data transfer. So decode logic cannot be used here, because during the address calculation the data flow is used. So you cannot have a decode stage here. Okay. So the cycles that access main memory are shown with a light shading. So you can see that on every stage the memory is accessed, because these are all the instruction accesses and this is the only data access. Now during this time, why there is no fetch here? Because now instruction is getting accessed. The data is getting accessed here during this cycle. So next instruction cannot be fetched, because if you have to remember that it is a one-ion architecture where same memory is used for instruction and data. Because data access is happening here, instruction access has to wait. So after the data access is completed, the transfer is completed, the fetch of the next instruction happens. So you have to understand this diagram by going to in terms of time and then see what gets completed in the different stages of the pipeline. So the data path is likewise used in every cycle, being involved in all the execute cycles. So data path is what I explained you about the ALU and the data barrel shifter, and decode logic is always generating the control signals for the next data path. And in addition to data path control signals for the data transfer also happen. So during this time, control signals for the data transfer also is generated here. That's why the decode logic is not being used during this time. Okay. So the gaps, just to make you aware, they are called bubbles in the pipeline because of one address instruction coming here, the store instruction coming here. There are two bubbles in the pipeline. So effectively, the throughput of this cannot be 3 instruction per cycle, because there is some during some stages some time frame, some stages are not active. Okay, so because of that. Because during this time only these two are active, so all the pipeline stages are not used. Here also only 2 stages are used, one more is not used. Whereas rest of the time all 3 are used here. Here all 3 stages are used. So only when all the 3 stages are effectively used for some instruction, the throughput will be equal to the number of stages in the pipeline. Otherwise, it will be little less than the expected value. So I am giving an example with the address 1000 and 1004, 1008. These are the instructions. Suppose this address add instruction was at 1000, then next STR would have been at 1004, and this would have been at 1008. Now you have to understand one more thing, that the memory is determining the flow, and the speed of the operation through the pipeline. If you look at this particular time frame, when the execution of the instruction which was fetched at 1000 is happening, the instruction which is getting fetched from the instruction memory is 1000 plus 8. Now what does it mean? During this execution time, the R15, that is the PC value, will not be pointing at the instruction which is getting executed. It will be pointing at 1 plus 2, that is instruction but 1. Okay, next instruction but 1. That means not even the next instruction but the next to next will be the value of R15. It is pointing at this instruction. So if suppose the programmer assumes when my instruction, that add instruction or whatever is getting executed, the R15 is pointing at its own address or the next instruction, it is not true. It will be R15 will be pointing at the second instruction from the current instruction getting executed. So any dependency on R15 in the assembly code needs to comprehend this pipeline effect during the programming. So when we talk about some instruction and their impact, we will be touching upon this. So please remember this particular case where the actual execution of this instruction is happening for this 1000, the instruction at 1000, the R15 is pointing at 1000 plus 8 to fetch the instruction from the memory. So this is the anomaly that we should be aware of as an assembly programmer. And just explain you that if there is a branch instruction, we will talk about what this branch instruction means. It means that it is jumping to the control flow is jumping to some other value. That means the branch instruction is modifying the value of R15. So it won't be same as what is getting fetched here. After this execution, the R15, that is the PC, will be loaded with a new value. So whatever it has executed or accessed prior to this has to be flushed from the pipeline, and a new instruction has to be fed from the memory, and the pipeline has to be restarted from the beginning. So these stages will have to be stopped, and a new instruction has to be fetched. That is the impact of branch instruction on the pipeline. So PC's behavior, one consequence of the pipeline execution is program counter which is visible to the user R15 must run ahead of the current instruction. How much it is ahead? Plus 8. Okay. So if suppose the instruction which is getting executed is a single cycle instruction, that means add, the first execution itself, the first cycle means when that instruction gets executed in the execution stage, the PC will be 2 stages ahead. Whereas, so this needs to be comprehended in your program, in assembly program. And if whatever instruction you are executing is a multi-cycle instruction and your instruction is also modifying the value of R15, then it has to be done very carefully, otherwise there will be unexpected, unpredictable results because of the pipeline influence on the value of R15. Okay. What I mean by that is, during the execution, if your instruction itself is modifying the value of R15, what happens to the current value, and then it is overwritten by your own instruction. So it is not known until it depends on the programmer what instruction and what operation the programmer has performed on the R15, because R15 is also part of a general purpose register which can be used as one of the operands also for any of the data processing instructions. So it is completely dependent on the instruction being executed. So that's why ARM says that it is unpredictable. Other characteristics of the pipeline: the branch instruction or branching by the direct modification of the PC causes the ARM core to flash the pipeline, I mentioned to you. And another possible reason could be interrupt. When an interrupt happens, after the instruction which is getting executed is completed, the flow goes to the ISR, the interrupt service routine, which could be accessed from the interrupt vector, and then it starts executing the ISR from some other address. So the pipeline needs to be completely flushed, and a new value based on the PC which is stored in the interrupt vector has to be loaded, and it has to start fresh. So on return from the interrupt, what happens? The pipeline will be refilled again with the instruction which was just after the completed instruction. So we know the ARM processor. We will talk about this. Don't worry about even if you don't understand this at this moment. we will be covering a whole one session on interrupt. So that time all these things will become clearer. But just want to, while I am discussing about pipeline, I want you to be aware that interrupts and branches could cause some disturbance to the pipeline, and it needs to be handled accordingly. So just to summarize, what are the limitations to the pipeline? Because of one-on-one architecture with a single instruction and data memory, we will have its performance limited by the available memory bandwidth. So ARM core accesses memory on almost every cycle, because it could be for accessing the instruction or it could be for accessing the data. So to get a better cycle per instruction, suppose you want to improve the performance, I told you because of the store instruction, one cycle was, or two cycles were missed out, two bubbles you saw in the previous cases. So if you want to avoid such penalty to the throughput, we need to do something. So maybe ARM7 has a limitation, but in the subsequent ARM family processor, they have split the instruction and data memories into separate, so that you don't contend for the same bus and compete for the same bus in the same cycle. So instruction access and the data access can happen in parallel if there are two different buses. So you may have a better performance there. So another way of improving the performance is improving the or increasing the number of stages in the pipeline. Why does increasing the pipeline stages improve the performance? That is, if you remember, if there was a 3-stage pipeline, the average throughput of the pipeline would be 3. Suppose if you subdivide it further and make it into 5 stages, the average throughput will be 5. That means 5 instructions may get completed every clock cycle instead of 3 in the 3-stage pipeline. So even if you are running the processor in the same clock, the M clock is same. Suppose it is 10 megahertz or whatever it is, a 5-stage pipeline may perform better than the 3-stage pipeline. Of course, it depends on the flow of instruction, but hypothetically, because of increasing the number of stages, we can still get a better performance. And that 5-stage pipeline is implemented in the ARM9 processor. It is not in ARM7. ARM7 is a 3-stage pipeline with a common instruction and data memory. Though our goal is to study only ARM7 TDMI in detail in this session, all these sessions, I wanted to cover some part of 5-stage pipeline also. So we will be taking a detour to ARM9 in the next section to talk about 5-stage pipeline, and then we will come back to ARM7 again to continue forward. So we will be talking about 5-stage pipeline of ARM9 in the next class, and just wanted to give you a flavor of where the ARM family processors are going. You can see that ARM10 family has a 6-stage pipeline and ARM11 family has an 8-stage pipeline. So you can see that ARM9 is stopped here in ARM7 itself, and going forward everything is hardware. That means there are separate instruction and data memory, and there are multipliers with complex operations in the latest feature family. So we will go to ARM9 only to understand the 5-stage pipeline in the next section, and then we will concentrate in the rest of the discussion only on ARM7 by going deeper into what are the instructions being supported in ARM7. Whatever you learn in ARM7 is relevant for the rest of the families of ARM4. So I am just taking a detour only to make you understand about 5-stage pipeline, and we will come back. Okay. So these are the topics that we covered in this session today. We touched upon data flow model, how particular instruction is decoded and how operands are exchanged, and then operation is performed in a single cycle. And I also explained about the clock cycle in detail, about 2-phase non-overlapping clock. And then we looked at instruction 3-stage pipeline, how different instructions get executed during the using the pipeline. And then we talked about 3-stage pipeline limitations, and then why we need higher stages of pipeline using comparison of multiple ARM family processors. So this brings us to the end of this session. I hope you enjoyed this, and these are the books I refer continuously for all the sessions apart from the ARM manual. And thank you all for your time, and hope you enjoyed this talk, and let us meet again for the 5-stage pipeline, which will be very interesting with its own problems also associated with that. Thank you very much, and have a nice day. Bye bye.